Thank you very much, Claudia. I think this is an excellent introduction to what we want to present today and the collaboration that we are having ongoing. We are specifically focusing on FLIM as the application with the main target to increase the speed. And very importantly, we are enabling both confocal and widefield FLIM. Just a short introduction on FLIM. FLIM is a method where we try to extract the average lifetime or the lifetime composition of a sample by using time-resolved imaging. It enables very good selectivity and identification of features of interest. Of course, the main benefits are that it's rather insensitive to the intensity of the fluorescence, and that it enables high contrast. On the other hand, the drawback is, of course, that it's relatively slow due to potential pileups that we might have in the system. And most of the, let's say, golden standard systems, they do require scanning systems, which are more complex than typical simple widefield systems. Dwelling a bit deeper into the instrumentation drawbacks and why the speed reduction. Of course, if you want to achieve a certain lifetime precision, we require a certain amount of photons due to statistics. So in case we have ideal instrumentation and we want to have 10% lifetime precision, we would need to acquire at least 100 photons. This is typically coupled with the pileup constraint, which requires us to have a detection rate which is typically 1 to 10% of the laser repetition rate. So if you would focus on a scenario which is depicted here on the right hand side, where you have a scanning system with a 20 megahertz laser, because of pileup you want to be at 10% of the repetition rate with your detector. And you want to have a resolution of 512 square and targeting the 10% lifetime precision, you end up with a FLIM frame rate of 0.08 frames per second. I also want to emphasize the third part, which is the requirement for systems. And we are going to touch upon that topic a bit later in the talk. Our solution for this challenge and targeting the increase in the FLIM frame rate is to parallelize pixels, and this can be done with SPAD arrays and image sensors. SPAD arrays are enabling a very good signal-to-noise ratio in the low-light scenarios. And what I would like to emphasize additionally is that signal-to-noise ratio is different from the sensitivity. So even if you might have a higher sensitivity of a typical photodiode or potentially an EMCCDs in image sensors, what finally matters is the signal-to-noise ratio. And this is really clearly depicted here, where the SPAD has around 50% sensitivity, but due to the lower contributions in noise, the signal-to-noise ratio is better. SPADs, or as many people in the microscopy community call it APDs as well, they have usage in three main application fields where we have low light. We are talking about single particles or quantum detection. High speed is very important. Of course, if you're scanning, if you have a confocal microscope, we are by default in a high speed mode. Then the extension of confocal microscopy is the beautiful technique of image scanning microscopy, or ISM. If you're then focusing more on wide field, we are talking about high-speed modes of SOFI or single molecule localization microscopy, which finally enable us to get super resolution images at a faster pace. The high time precision of SPADs and SPAD arrays and image sensors frame it to be ideal detectors for FLIM. Specifically for bioimaging technology, we are offering SPAD arrays and image sensors. So on the bottom, you can see a SPAD array with 23 pixels and a SPAD image sensor with 512 by 512 pixels. On the right-hand side, you can see the typical specifications with photon detection probability higher than 50%. I need to reiterate that all our sensors are microlens based, so the fill factor is extremely high. Dark count rates are below 100 counts per second, and for the image sensor is even lower, so it's typically less than 25 counts per second. SPAD image sensors are operated in a mode which we call time gating. Time gating enables us to have very short gates, minimally 6 nanoseconds, which can be then shifted in phase by 17 picoseconds. This finally enables us to recreate the timing distribution of the fluorophores, fit the exponential, or just use some simpler methods. If you're talking about SPAD arrays, so here I'm referencing the 23 pixel array, then we operate the sensor in time tagging mode, where we can get exactly the position of the photon and the exact time of arrival with typically 5 to 20 picoseconds resolution. On the bottom, you can again see the beautiful micrograph of the chip. So how does that couple now with the imaging speed? Talking about two different illumination modes. The first one is the classical illumination mode, where we would just open a bit the pinhole or even close it, and we would have airy disk illumination. We approximate that in this mode, the central pixel would receive around 20% of light. The remaining pixels would receive 80% of the light. By default, we are then increasing or we are reducing the pileup constraints by a factor of 5, and we can increase the FLIM frame rate by a factor of 5 equivalently. If you would change the illumination pattern or the detection pattern and have light uniformly hitting the whole SPAD array, we would increase the frame rate by 23 and reach a frame rate which is around 1.8 frames per second. Then if you would switch to SPAD image sensors, and results are going to be shown later, because of the tremendous parallelization operating all the pixels at the same time, we can go even higher to 30 frames per second. And now in the specific context of the collaboration and application use with PicoQuant, I'd like to focus here on the area disk illumination and enabling image scanning microscopy, which I believe is a very interesting topic, very hot topic recently. It enables higher image resolution going beyond the diffraction limit, and of course higher speed of FLIM acquisition. So with that, I'd like to switch the talk or the lead to Johan from PicoQuant.
Yeah, thank you, Michel, and thanks to everyone for staying this long and giving me the opportunity to show a few application examples for these next generation SPAD sensors. So what PicoQuant is probably best known for is the confocal microscopes, which are still workhorses in many biology lab and an important part of imaging facilities. And that is due to a few key advantages of confocal microscopy, which gives a diffraction limited resolution, as you can see in the plots here on the top. The intrinsic physical sectioning, which is a huge advantage of confocal microscopy, and then combined with the right timing hardware, can give picosecond precise temporal resolution, so giving us the lifetime information as well. And confocal microscopy additionally also offers the option of even better sectioning and lateral resolution by closing the pinhole in front of the detectors. But in reality, this is almost never done in practice, because by closing the pinhole, light collection efficiency is sacrificed, which is often not possible in biological applications. So what this means is that the typical confocal image, here you see a U2S cell line where tubulin is stained with one fluorophore, TOM20, so the mitochondria are stained with another fluorophore. And the typical confocal image would look like you see in the example here. Now, this can be combined with the detector that Michel just presented. So in collaboration with PicoQuant, there was this 23 pixel SPUT developed, which is then combined with the PicoQuant TC-SPC, so a multi-channel TC-SPC up to 64 channels. Of course, in this case, with the 23 channel detector, typically we would use the 32 channel multi-harp, which then combining the detector and the multi-harp gives us very good timing performance, 5 picosecond resolution, and a total IRF with excluding the laser of sub 120 picoseconds. And this combination of the 23 pixel detector and the multi-harp combines very well with the PicoQuant environment, is directly compatible. And what this gives us now is the opportunity to do image scanning microscopy, meaning that we replace the typical confocal detector of a pinhole and a large detector now with a pixelated detector. And that means the pixelated detector in this case has the size of approximately 1 area unit, so similar to what the confocal pinhole would typically be, meaning that we collect all the light collected in a confocal microscope, but the pixelated detector gives us additional spatial information. And that can be used, as you see in the middle, the confocal image as compared to the image scanning microscopy. I won't go into too much detail about the data processing, but I think you can appreciate very well that you can see the hollow structure of the mitochondria. You can see the microtubules much clearer with a lot of out of focus contributions removed. So the bottom line is basically that image scanning microscopy, this idea pioneered by Shepard and now and many others, allows us to use basically the confocal with the closed pinhole performance, but collecting all the light that would fall into our 1 area unit pinhole. This gives not only better lateral resolution, but also improved sectioning, and that you can appreciate very well in this video, where the color scale now encodes the Z information, so the height in the sample. And here you can see that comparing on the left the pseudoconfocal, so what we get when we sum up the signal from all 23 pixels, to the ISM, which includes the improved sectioning, you can see the 3D structure much clearer. And an important thing I should highlight here is that this is not using the 3D information, it's just using 2D information on any individual Z slice. So this is the kind of the 3D here is just to highlight how well the sectioning works, but this is the sectioning quality that one can achieve on a single Z slice. So this 3D is very useful to appreciate the improved sectioning with ISM. And on the next slide, I wanted to highlight also the improved lateral resolution that can be achieved with ISM. So here we have a slightly different sample, which is now excited at 485 nanometers. Also U2S cell, where alpha tubulin is now stained with IF488. And on the very left, you can see again the pseudo confocal, so a confocal-like image where all 23 pixels are just integrated. And then next comes the ISM. Sorry, can you go one slide back?
Yes.
And the image in the middle, you can see the added ISM processing, which improves resolution. So you can see you go from 190 nanometers to approximately 160 nanometers. And also here you can again see the improved sectioning, which removes a lot of the out of focus blur. And then in the last step, you can also deconvolve this image on top to get a resolution of 120 nanometers. And to just quantify this a bit better, we try to then look at basically points in the image where we have two microtubule strands converging very well, where you can see the resolution and quantify this somewhat better. And as you can appreciate on the left, in the deconvolved ISM data, the two microtubule strands, which are approximately 120 nanometers apart, can be quite well separated. And this is also corroborated by a Fourier ring correlation, which gives us similar results of about 125 nanometer resolution. So this is basically what one can do with state-of-the-art image scanning microscopy. But then the main advantage of using the spot array for this is that all of this naturally combines with the time resolve detection. So here we have yet again a third sample where two species in the sample are stained with two different fluorophores. Alpha tubulin is stained with a bi-exponential fluorophore, and TOM20 is stained with the mono-exponential fluorophore of a longer lifetime. And you see on the top left, again, the pseudo-confocal image, where you can already appreciate that this is maybe not the easiest sample to do species separation based on lifetime, since in this image, mainly microtubules are visible and the mitochondria seem much darker. But then separating this by lifetime and processing the entire, so both separated species with the entire ISM workflow, you can see that even for this challenging sample, where the one species is approximately 35 times brighter than the other species, we can get very nice species separation based on the lifetime, showing in the middle the microtubule image, also processed with the entire ISM workflow, giving improved sectioning, improved resolution. And on the right, the much darker microtubules, which we can separate almost artifact-free based on the fluorescence lifetime. And just on the bottom left, you can see the overlay with the mitochondria in green and the microtubules in red. Appreciating this gives us basically, even in this very challenging case, we can get very clear species separation, even in overlapping areas. And with that, basically showing that these detectors can prove very beneficial in this kind of FLIM applications, I think I want to hand back to Michel, who will show some more FLIM data.
Thank you very much, Johan. Great presentation and results. And I would like to just, before finishing with the presentation, have a short peek into the widefield FLIM results. On the top, you can see the FLIM results, so intensity overlaid with lifetime information decoded in color. At the bottom, you can see the histogram of lifetime, which should directly indicate also the precision, because the sample on the top was labeled only with one fluorophore. You can also see the frames per second highlighted. This is also including all the system overheads of saving and loading data. And really the highlights and the key message here is, with widefield FLIM enabled by spot image sensors, we have a tremendous data or photon rate that we can support. So while we are talking about mega counts in scan systems, for widefield systems, we are talking about giga counts. And this is finally the direct link of why the frame rate is improved. Okay, with that, I would like to thank you for your attention, and if you have some questions, we'll be happy to take them.